Hey guys, this is going to be a short little synthesis video covering just a couple tips for synthesis, how you can be a little bit better at it, how you can make better guesses, whatnot. I know that synthesis is a bit daunting, a bit scary. It's the culmination of all OChem, right? You take all the reactions you've learned and kind of throw them all together and make something out of it. So that can be a bit of a scary task or a big ask of a student at the end of the quarter, especially this quarter, right, where you've got to teach yourself a lot of things. So point of this video is just going to try to get you exposed to a lot of the important transformations and really just the patterns that I look for in synthesis. So this actually, this page shouldn't be here, it's blank. So I guess you could just scratch, but yeah, so there's like 10 problems on here. Kind of just randomly threw them on here in terms of difficulty. I didn't really think about them. I mean, really these last two are just fun ones, especially this last one. It's a really fun one in my opinion. But yeah, so these problems really are just aiming to show you guys patterns that I look for, just in practice problems and even just in real life, right? Patterns I look for in molecules in real life when I'm trying to think of how to make something and what real scientists use every single day. Okay, cool. So because synthesis is the culmination of all reactions, it's really, really important that you at least have a grasp of what reactions are possible, okay? You don't need to know every single reaction. You just need to know what is possible. Unfortunately, I don't have the time, right, to sit here and walk through every single reaction that you guys should know. But I will provide you guys with a small little overview of what you should know. That way, at least if you're following along to this video completely clueless, you have somewhat of an idea of what's allowed and what's not. Okay, so beginning of the quarter, right? What did we start with? We have an alkane chain and we can functionalize it, right? We can take this hydrogen here and we can functionalize it with the halogen. Okay, so that was our radical halogenation. So that was something we could do. Very first reaction, right, is we add a functionality to nothing. And so with this, we made the alkyl halide, which was the perfect substrate, right? We could do SN2 with these guys. We can do E2 with these guys, substitute the halogen or make a pi bond, really. Okay, so we can do these two types of reactions. And so a majority of midterm 2 was, hey, if I had a certain, halide molecule and I exposed some nucleophile, what would I get, right? So transformations that are allowed, making pi bonds and adding nucleophiles. But these were kind of dead ends for us, right? There's nothing much more else you could do. I mean, I guess with certain SN2 mechanics, you could kind of manipulate stereochemistry. Pi bonds, you can't really do much with them. So at least at that point, this was kind of a dead end. Well, if I chose to make my molecule an alcohol, right? Well, then we learned a little bit about alcohol chemistry. So maybe my substitution is an alcohol. So we can make alcohols. Now, the way to think about alcohols are groups that want to be halides, but they aren't, right? If I try to do reactions with them, well, these guys are a little bit pesky, right? They're a little bit, resistant to reaction. So a majority of alcohol reactions is, just adding some kind of group to it that transforms the alcohol into a pseudo halide, or makes it like a halogen, and suddenly we can do all the reactions we want to, whether it's SN or E. Okay, so alcohols almost there, right? They're almost good, but we need to help them. We need to make them better. I mean, if you think of every single alcohol reaction there is, it's you're adding something that makes it a better leaving group, and then it does the reaction you want it to do, right? Whether that's adding a proton to make it water, or adding something inorganic like phosphorus or sulfur, right? And just making it a better leaving group overall. Okay? Even oxidations, right? Chromium adds to oxygen so that, not that it makes oxygen a better leaving group, but it helps facilitate that oxidation pattern. Okay, so just tips on how to think about these reactions. In OChem, it's really important that you start to see patterns like this really, really soon, because in 118A, it's really easy to sit down and memorize everything, but in B and C, where you're learning the same amount of reactions you learn in 118A every single week, right? It's going to get a little bit more difficult. So you really got to look for patterns to help organize this information. Oops, sorry, I forgot to put my Python there. Okay, now with the introduction of alcohols, right, we also introduced oxidations. So like oxidations to aldehydes or ketones, depending on the type of alcohol we have, right, to even oxidizing to carboxylic acids. Okay, so one key thing in synthesis is looking for things that can only be accessed one way, right? Or the best way to make them is only one single pathway. Oxidations are only one, there's only one way to do these in this class. So if we ever see oxidations in our syntheses, hey, I think that oxidized center probably came from an alcohol, right? Because that's the only way I know how to do it. So carboxylic acids, we're looking at you. Now, generally, right, there are some differences. I'll just note them down here. Jones should really only ever be used to make carboxylic acids, but I guess you can make it for ketones if you wanted to. PCC is like a very mild, like we're trying to stop our reaction very, very early or stop our oxidation, right? Cool. And so with that being introduced, the oxidized centers, then we talk about reductions. So we can have a carbonyl and we can choose to reduce a carbonyl into an alcohol, right? Either to remake that alcohol. So these are our hydride additions. So we have NABH4 and we have LiAlH4. So I'll just write these guys up here. Okay. Or, right, I could take a carbonyl and I could add an R minus. So that's like my RLI or RMGPR. Now, just like we just mentioned for oxidations, this reaction here is also one that if we see it, we know exactly what it is. Grignards are incredibly important to the synthetic sphere, okay? Because it is the first and only reaction in this class where we can make a carbon-carbon bond, okay? Carbon-carbon bond. Insanely important, insanely important. So anytime we make a carbon-carbon bond in any of these syntheses, I want all of you to instantly think, that is a Grignard, okay? That is a Grignard. We just gotta learn how to access it, okay? One important thing with the Grignard is that it has sort of a caveat, right? You always make an alcohol. So when we're thinking about our end product and maybe there's a carbon chain, we want to think, well, hey, if I formed a carbon-carbon chain, right, where is the alcohol associated with it, right? Finding your alcohol, that's a good pattern, okay? Now, after carbonyls, we talk about ethers. And so generally speaking, ethers aren't really cool in synthesis. Like we don't really use them synthetically, maybe in a conceptual problem, but we don't really, because they're usually solvents, right? Like for Grignard, they're usually a solvent. But epoxides are really, really good, right? And so generally epoxides, we make them with these alpha bromo alcohols, right? They're in a little bit of base, and we can make an alcohol. Sorry, we can make an epoxide. What am I doing? There we go. All right, epoxide. And so epoxides in acid open up on the more subside to some nucleophile, and in bases open up to the less subside. Okay. So epoxides are very, very interesting, right? Because not only do they give us, right, an alcohol, but they give us a second functionality. Okay, we'll talk about this again. We'll talk about this more when we get to epoxide problems. But if we look at the alcohol and the nucleophile, one thing I like to note is that they have what we call a vicinal relationship. Okay, so what does that mean? Well, if I have the alcohol's carbon 1, then right next door on carbon 2, we have a nucleophile functionality. Okay, this 1,2 difunctionality is very, very characteristic of epoxides. Okay, so if we're doing problems and we see a 1,2 difunctionalization, right, like we see maybe one carbon being functionalized and the next door carbon being functionalized, I want to think that an epoxide was responsible for that type of behavior. Okay, now epoxides, I guess they're kind of given away because the only way to make them is this guy here, and you guys don't really have a good way to make them, but it's still very good to recognize the species because, hey, if we know how epoxides work and what type of relation they give us, right, we're better at identifying, the correct reactions for our problems. Okay, cool. So again, this was a super, super coarse, super, super superficial overview of the material. This is definitely not as in-depth as you want it to be, but it should get us through should get your brain juices flowing. And if it doesn't, it's okay because we'll talk through every single problem and how to solve it. Okay, so generally, these are the reactions that we want to know, or at least understand that these reactions are possible. These transformations are possible. So when we're going through our problems, we'll have a bit of an easier time, right? Understanding what is allowed and what isn't. Okay, cool. All right. So Every single problem, you're welcome to pause and try it on your own. I'm just going to do it as if I'm doing it and kind of walk through the process. So my synthetic process is something known as retrosynthetic analysis. And so a couple of you might have heard about this, maybe tried it, didn't like it. I really encourage you guys to please give me a chance and help show you guys the light. Retrosynthetic process is the best way of doing synthesis, in my opinion. And not only my opinion, I mean, it's done as industry as well. And it's really, everyone is doing retrosynthetic analysis when they're doing synthesis. If you're doing it forward, you're doing it like inefficiently. So allow me to give you guys a more efficient way to do this. Okay. So retrosynthetic analysis, what is it? The point is we start at the product and we look for patterns, or we look for things that tell us about the transformations that were taking place or that are allowed. For example, I'm starting with a square, right, 4 carbons, and I'm ending with a butane and this oxide function here. Okay. As I've already kind of noted, right, I can already see that the 4 carbons in that butane are probably the 4 carbons that were in my cyclobutane. Okay, so one thing I can already mentally note is that I'm going to crack open this cycle here. Okay, in this class, there's only one way to crack open squares and triangles, right? That's H2PD. So it might just help to even start to sketch a little bit of the synthesis. Okay, so we can get that there. From here, right, I try to compare where my functionalities are and what are things that I can allow that functionality to happen. For example, I can see that I'm functionalizing on that second carbon, right, on that second carbon, right, this carbon here, okay? And I'm not making a pi bond, but I'm adding, an oxygen, right? Remember, early on, what were the reactions we've mainly learned? We learned substitutions and eliminations. So eliminations, what makes them very, very obvious is that there's a pi bond, right? So I want to think elimination, if there's a pi bond. But in this case, there isn't an elimination at all, or there's no pi bond at all, so there can't be an elimination. So this has to be some kind of substitution. So I'm thinking now that this ethoxy piece here, this new component to my 4 carbons, was added in a substitution. Which means that if it were added in a substitution, I could sort of cut this bond here and say, hey, I had a 4 carbon chain with some group that could have been substituted by my ethoxy group. Okay, now we can figure this part out, right? That X group is probably going to be a halogen, right? That's the best leaving group, right? As we use a halogen. And so if I think about it on that second carbon there, whether I want to use chlorine or bromine is kind of arbitrary because the math always works out. Bromine and chlorine both like secondary carbons. I will just choose Br2 here just because it's a bit of a safe option, right? Because I know it's going to go on that more so majority of the time. Okay. Now here's where things are a little tricky, but again, we can use our rules to figure this out, right? Our ethoxy nucleophile that ends up substituting the bromine comes in 2 flavors, right? It comes as the oxide or it comes as the alcohol, right? So which one do we want to use? I think there's one that some people like to tend towards because it just feels like right. Okay. The ethoxide, as we learned, is a very strong base. And generally, if it's going to do a substitution, we'll do SN2, right? But again, it's a strong base. So think about what a strong base likes to do. On the other hand, right, our ethanol is a very weak base and it's a weak nucleophile. Right, so this guy is going to do SN1. It's a solvent molecule, right? It's a new solvolysis. So when we look at our carbon here, right, our secondary carbon here, we want to think, is our secondary carbon going to allow us to do one of these reactions, right? Or is it not going to allow us to do one of these reactions, right? Is a strong base going to do SN2 on a secondary, right? Is a solvent molecule going to do SN1 on a secondary, right? That's the question we have to ask. Now, in this case, strong bases love to do E2 on secondary, so this is actually not going to work out, right? Because this is going to do E2, but we are allowed to do SN1s on secondary centers with solvent molecules. So we can go ahead and do an SN1 over here. Okay, cool. So this was a bit of a warm-up problem, right? A bit of a, get your brain jogging. But this is the idea, the basic idea of a retrosynthetic analysis, right? Look for transformations you understand and look for the new components. right? If you can trace out what your starting material is and then base, oh, okay, I think that this stuff is new and it's functionalizing this carbon, sort of walk yourself through what transformation can happen, you start to allow yourself to see, oh, right, the correct pathway to make these things. Right, brute forcing it from the beginning. I mean, for a problem like this one, you could totally have brute forced it, right? You could have just said, "Oh, H2 is the only thing I can do to crack open that," right? If I have an alkane, right, 99% of the time I'm just going to functionalize it, right? This first problem is a very brute forcible problem, but future problems are not going to be as brute forcible. Okay, so even with a simple one like this, we do want to take that retrosynthetic pathway, even though the forward is kind of there. So let me just reiterate this point as well, because it is a good one, right? Like some little tips, right? H2PD, always use it to break open a square or a triangle, right? Square or triangle, always use that to break that open. Really the only ways to do that. And whenever you have an alkane, functionality is key, right? Alkanes need to be functionalized. X2 is always going to be sort of your go-to for that. Now, generally speaking, BR2 will most likely be your best choice, unless you have a weird example like this one where you have to choose between functionalizing here versus here, right? Where the math works out that if you want on that secondary position, you go with like chlorine or something, or right on this one, if you wanted to go on the tertiary, go with bromine, right? Something like that. Okay, cool. So little tips and tricks. All right. Moving on, again, brain jogger. Cool. So after this first one, that was supposed to be more of a brain jogger. This one's like a midterm 2 type of synthesis. The rest of these are going to be more finals related. Okay, so we're going to do a lot more of what's expected on the final. And what you'll also notice is that we're going to use one transformation kind of over and over again, because it is probably the most important transformation in this class. Okay, cool. So for you guys that want to, go ahead, try this on your own. For those of you that want the support in going through this, let's go ahead and go through this, okay? So first off, the first thing that I noticed, right? I noticed kind of two things, right? One thing that I noticed is that, wow, I started with 2, and now I have 6 carbons. So I formed a bunch of CC bonds. Only one way to do that. That is a Grignard, okay? So I'm going to be doing a Grignard reaction in this synthesis. Okay, now remember, Grignard has a caveat, right? It always comes with an alcohol. When I look here, I don't see an alcohol. So maybe the first thing that we can think of is, where in the world did my alcohol go? Well, this goes to the second thing that I noticed, and that's the pi bond. If I have a pi bond, right, I know that I did some kind of elimination reaction. So I did some kind of elimination. So alcohols are able to be eliminated. And so I'm thinking, okay, maybe I did like an H2SO4 reaction on an alcohol to form this pi bond. Now, it's not directly clear immediately to me which carbon is alpha and which one's beta, but I'm just going to choose for it to be that way, okay? Because it could have either been here or it could have been here. Now, as we'll see with the synthesis, it actually doesn't matter which one I choose, okay? I'm actually just going to choose this one here, just because, okay? But I'll, after this, we'll go through the other one and we'll see it really didn't matter which one we chose. Okay, cool. So alpha and beta, and we got our alcohol. So noticing those two things about our, substrate kind of helped us, narrow it down to what was the most likely previous intermediate. Okay. Now I know some of you guys are gonna be finicky, so tertiary, I'll go ahead and put 100 degrees Celsius because I think that's what you were told is the elimination temperature. Which okay, I'll accept it. Okay, cool. Now that we've gotten to this point, right? We've gotten to the point of okay, we have our alcohol, so this is a Grignard, right? Now we have to think about which 2 carbons do we think were the ones that were the original 2 carbons, right? Because there's 6 of these carbons, right? So which 2 do we think are the original carbons? Well, if I choose these 2 carbons here, right, as my original carbon, right, I don't have any functionality on these carbons other than having added this carbon chain here. Okay, so I could totally choose those 2 to be my 2 carbons, but I want to be able to track some functionality. Okay, so I can make you can make the same argument here, right? There's no functionality on them, and I want to be able to track my functionality. So I personally feel more comfortable saying that these 2 carbons here were my original 2 carbons because I can track this alcohol functionality on them. Okay, now some of you may not be comfortable with that sort of reasoning, and that's totally okay, because again, we'll go through this at the end, but you could have totally chosen this or this. Okay, there's actually a bit of a, for those who try it, there is a hack, right, that you can use that makes this okay. But in order to, to really ingrain the retrostatic process, it's really important we understand that, hey, when we're doing this backwards process, we try to track our functionalities, right? Try to, make sure they make sense where they're going. So to me, it makes sense that these 2 carbons that have the alcohol are going to be the 2 carbons in my original molecule. Okay. Now, if I take that guess, that must mean then that these 2 carbons here are new. So it is these carbon-carbon bonds that are the new bonds that we formed. Okay. So Grignard can only be added one at a time. So I'm going to go ahead and say, okay, let's cut this bond here and say that I added this blue part as an ethyl Grignard. And so here's a cool little tip. Okay, now for this particular synthesis, it's not, it just, most of you might be able to see it, but I still want to show you this trick just in case you have a hard time seeing it. But if you're ever curious as to whether you use a carbonyl, right, whether your alcohol came from a carbonyl or it came from an epoxide, because remember, either of those 2 can react with Grignards. Here's a little trick you can do. When you cut this bond here, right, so this is your new carbon chain, cut the bond with your with these carbons here, put a cation. So actually, first let's draw the molecule out. So it looks like this. You put a cation underneath the carbon from which you cut a bond. So we cut a bond from this carbon here, so put a cation on it. If the alcohol is right next door, or the cation is right underneath the alcohol, that means that your substrate was a ketone. Okay, so that's how we can figure out that a ketone was used in order to do this transformation. Okay, so it's a cool little, it's a neat little trick you can do if you're a little, if you're not confident in whether it's a ketone or an epoxide. Okay, so again, the carbon from which you cut that chain, so this carbon here, just put a cation on it, right? So underneath, so I know that this came from a ketone. So I'll just go ahead and draw that. Okay, this is the ketone that we added our Grignard to. Okay. Again, when we get to epoxides, we'll see a different pattern we can use to figure out for epoxides that we use in epoxide. Okay, so this is the guy that added on. Now, to be totally correct, I'll go ahead and put the total conditions here. Cool. Now that we're back at, now that we have our ketone substrate, again, where do ketones come from? Where do we see this oxidation? It's only one way, right? We must have oxidized some alcohol. So we get to this portion here. And once again, once we've uncovered our alcohol, I am tracking these 2 carbons, right? I'm tracking these 2 carbons. So these 2 carbons here could have been, or, are going to be what I say are my new carbons. And if I cut that bond, so I'm saying that I used this guy here, right? Again, from where I cut that bond, right, that carbon bond that I'm cutting, right, I can put a cation there. And if the alcohol is next to the cation, this must have been a carbonyl. Okay, and so this is an aldehyde. Where's that oxidation coming from? Right, that oxidation has got to be coming from a PCC step. And so that must come from an alcohol. And if I look here, right, now I've simplified it down to my 2 carbons, right? How do I make an alcohol from an alkane? Well, think about it this way. Can I just add an alcohol to an alkane? No, I can't, right? The only thing I can add straight up from an alcohol, straight up to an alkane is going to be a halogen. And then from here, I can do, right, a substitution, right? Because I'm turning X into OH. Now, it doesn't matter who X is here because it's a CH3, right? Who cares? Choose either one. Maybe CO2 will be faster for this one. It really doesn't matter. But from here to here, right, we're substituting OH with X. So I asked myself the same question. Should I use OH minus, which is a strong base, and would have to do SN2 for this? Or do I use water, right, which is a solvent I'm going to have to use SN1 for this. Okay. Shouldn't be too hard. This is a primary carbon. You cannot do SN1 on a primary carbon, but everything practically does SN2 unless you're like a bulky base, right? So we can totally use NaOH in water here. Okay, cool. So this synthesis is a little bit interesting, right? I kind of took, sorry, dry throat. I kind of took a long-winded path on this, but again, what's most important is how we're tracking our carbons and how we're explaining where things came from. Okay, Grignard, again, super, super important reaction in this class. I'm almost willing to guarantee your final synthesis, at least one of them will have a Grignard involved. Okay, so it's really important to understand how we can track those carbons and how we can explain to ourselves where they came from. Okay, now, two things that I promised that I would talk about, right? One thing is I said, hey, it really didn't matter which alcohol we used, right? Why is that? Well, I could have started with this guy here and said, okay, I'm going to track the alcohol on my starting two carbons. So let's say it was this. So then, therefore, these 4 carbons here are my new carbons, right? Well, I can go ahead and cut here again. And hopefully you're convinced now that this would have been an aldehyde that this came from. And this could have been my Grignard here. Okay, so this could have been my Grignard. That totally works. Okay, and so now you might be thinking, oh, wait a minute. So you're telling me that I could have literally just started from here, right? It went this way. Yeah, that totally works, right? Unless there's some rule, unless there's some carbon constraint imposed on you guys, you're more than welcome to use a pathway like this one. And then you can do again like an H2SO4 at 100 degrees Celsius, right? To get your alkene that's preferred, right? Your preferred alkene there. Okay, that's totally possible. Something you could have done. Okay, so yeah, that works, right? If you saw that and you did that, great, right? Don't think that you did anything wrong, right? Yeah, that's also very possible. The other thing that I said I would explain is, why am I saying that I have to track the alcohol? Well, you really didn't have to, right? I could have taken, I guess I'll do it up here, but I could have taken, right, and said that these two were my original and that everything here is new, right? It's just that if I do that, right, and I cut this, well, hey, then I'm saying my starting material is this Grignard and my ketone is the reagent that I added, okay? That's also totally fine. That's also totally fine. Okay, so that's something I could have done as well. Okay, so why is it then? So it seems like I really chose not to take shortcuts here for some reason, right? Because I guess for this one, what I could have done was just added an Mg and ether and then just made the Grignard here, right? And then I could have kind of gotten here, like I could have gone all the way here for free, right? That's something I could have done. It's like, dude, what are you doing? Why did you take this long-winded pathway? The reason why I did the longer pathway, right, is because there's something about this longer pathway that makes it a little bit better. Okay, on some of these exams, you will sometimes be asked to make every carbon-containing reagent that you use. Okay, so for example, right, X2 is not carbon-containing, neither is NOH, neither is PCC, but this Grignard is carbon-containing. You could be asked to make that. Okay, so I mean, we showed how to make it. We showed how to make it this way, right? We just did this here. So you're taking your simple unit and you're making your Grignard from it, and you're making your aldehyde from it, right? You're doing your 2 Grignards, and then you're doing your dehydration. So sometimes, again, you'll be told, hey, if you're going to use a carbon-containing reagent, right, you have to also make it. This is the pathway that kind of highlights that, right? It is not very easy to make this guy as a reagent or this guy as a reagent from your starting material without using carbon-containing reagents. It's a bit long-winded. I can imagine there's a bunch of you that can figure it out, right? And can do it. I mean, I guess I can kind of see what you could do here. You could probably, I mean, you'd have to get at least this far, right, to even consider using this blue guy, right? Because you could just oxidize this, I suppose, right? And then you could condense with this guy. But you'd have to get this far anyways to do that. Oh, wait, sorry. It's right here. like you have to get this far anyways, right? But you've kind of already done that, right, with this synthesis going this way, right, making all those reagents. So here's my advice. If you have to, like, read the directions, obviously my number one advice, but if you have to make, right, all the reagents, try to, reduce this down to its simplest units. Don't just, look for some shortcut, because those are, I can almost guarantee to you that when you get a simple synthesis like this one, it's in every professor and TA's mind that, there's a shortcut, but we're trying to reduce the usage of that shortcut by asking for you to make everything. Okay, but if there's no constraint, then by all means use the cheats, right? The cheats are great. I mean, look at this one, right? Like by assuming that this here was your original starting piece, right? Like we did over back here, right? You can literally reduce the synthesis to like 1, 2, 3, 4 steps, right? As opposed to this long-winded here. Okay, so again, for any of you that felt like, oh my God, why didn't he do this? Why didn't he do that? Why is something wrong? Nothing's wrong at all, right? Everyone's right. That's the great thing about synthesis, is that there's usually a lot of answers to them. Okay, cool. So a first taste of Grignard, and in particularly a good example, we will be seeing Grignard for a lot of these, because again, Grignard is such a powerful reaction. It makes the CC bond, the organic chemistry bond. Okay, cool. Right, so go on to the next one. Oh, okay. So in the flavor of Grignard, I bring up this problem because Grignard is kind of an interesting species, right? So I guess I've kind of given it away what's going on here. So if I look at this problem, I mean, I'll of course try it, especially since I'm now giving away that Grignard's involved. Go ahead and try it. But for those of you that are, sticking around to hear me talk about it, right? Looking at this reaction is so weird. I have a chlorine, and somehow that chlorine disappeared, and then I added a bromine. Like weird things are going on. So let's try to break this down a little bit. Okay. Well, first things first, retrosynthetically, no carbon chain added, but right, I do have this 5-carbon chain with a bromine on that tertiary position. This reaction, the last reaction here is pretty obvious, right? That would just be a Br2HV, right? What other reaction puts bromine on a tertiary position? It's got to be a bromination. So I know that this should have been the previous molecule, right? Because Br2HV would add this. So the question becomes, how in the world do I turn chlorine, or how in the world do I get rid of chlorine, right? Or how do I turn it into a hydrogen? Okay, so you might want to think about this for a little bit, maybe even look in your notes. Okay, but the way that we're going to do this is using a Grignard. Okay, so how's this going to work? Well, you can add an Mg in ether. Turn it into this. And then I'm going to add water. Well, what? Why am I adding water? Well, remember, Grignard, right? Even though it is a nucleophile, they try to use it as a nucleophile, it is a very strong base, super strong base, super strong base. Okay. And so because it is a super strong base, if I have any sort of protic thing in my molecule or in my mixture, that protic thing and Grignard are going to react. In fact, Grignards are so reactive that if they make contact with the air, which has moisture, which has water, it will ignite. Okay, Grignards will ignite with the water in the air. They are incredibly water sensitive. Okay, protic sensitive as well. So generally speaking, Grignards are not compatible with protics. Okay, because they will instantly react, right? If I have a carbonyl and I have a water molecule, right? Even though I want to react like this, I'm actually going to react like this. And so what you're going to create is, you're going to, carbonyls will stay the same, but you're going to protonate your Grignard molecule. And you're going to end up with whatever, if it's water, then you end up with OH minus, right? It's a very violent reaction. Okay, now we can actually use this to our advantage in this reaction, right? Because if I introduce, again, water, that's protonating my Grignard. I'm doing an acid base. I'm essentially removing functionality. So imagine you're a scientist and, you chlorinate this molecule, or I guess you chlorinate this molecule, right? And you realize it was a mistake. You need to brominate it. Well, you can kind of get back, right? You can throw in a bit of magnesium, throw it in some water, pray to God, pray to whoever you pray to, right? And hopefully it undoes your mistake. So now adding to our synthetic toolkit is the idea that I can change H into X, right? With an X2. I can then remove X, right? I can defunctionalize a center by adding an MG, turning it into MGX, and then hydrating it, right? Or throwing it into some water. Okay, so we can now defunctionalize centers. So we can just start from the beginning. This is a cool little thought process, right? It's a cool little thought experiment, really what this is. And so have this one in the back of your minds, because sometimes you can do cool little tricks like this one here. Okay, a synthesis like this one, again, not very practical, but it's very thought-provoking. It makes you think about the chemical properties of the things you're learning about. Okay, cool. So cool thing here. Now, as you might have learned in lecture, I put D2O here. It would have just like turned this into a deuterium. That's all I would have done. So there would be like a deuterium here, if it were deuterium, but something you can do, right? Something to keep in mind. Cool. So just to kind of clarify, to make sure this point is clear, right? I'm not saying that Grignards cannot react in like water or anything, but the point is that if there is any water or anything protic, they are going to react with that thing. So you can imagine a good predicted products be something like this, right? CH3Li, H3O plus, right? With this hydroxyketone, right? A lot of you are going to want to hope that this reaction happens, but that's not what's going to happen at all, right? What's actually going to happen is you're going to deprotonate on that alcohol there. Okay, so the actual answer to this molecule, I mean, step one, right? Step one would give you this, right? That deprotonation. Step two, right, which is protonated back. So it appears that nothing happened, but two things did happen, right? We made CH4, right? We made methane, like we're like a cow or something. It's almost like we go to school for cows or something. Or do cows look like? I don't even remember. Whatever. I just know they have spots on them. Whatever. So it's like it's like we made methane and we just ended up with the same molecules. So something did happen in that sense. There's no reaction. It's just didn't do the reaction we intended. Yeah. Cool. All right. So cool little thought experiment problem there, that one. Cool. All right. So on to this one. Again, try it out if you want to, or you can stick around so we can talk about it. So again, I'm looking at this 3 carbons, 6 carbons, right? Obviously, some kind of Grignard just going on here. So CC bond formation. But again, Grignards, right? I see these new carbons, right? CC bond. So I know it's Grignard, right? That comes with an alcohol. So where's my alcohol? All I have is a bromine. Well, just like with the pi bond example, I can turn alcohols into bromines. That's totally possible. So I can say, hey, I think that I substituted this bromine, or I substitute alcohol with the bromine, right? Tertiary center, best thing you can use probably is HBr, right? You could probably get away with PBr3, right? You could probably get some partial on that. I guess it's not, well, I guess it's a multiple choice exam, so we couldn't get away with it. But remember, HBr is our SN1 type and PBr3 is our SN2 type. So it's better to use HBr onto tertiary centers. Okay. But now that we're here, we have our alcohol, right? We can start to talk. Hey, okay, where are my new carbons and where are my old carbons, right? So this is my original chain here, right? If I had to guess, right, I'm going to guess that it's these 3 carbons here. And this is actually a pretty good guess because, again, if we look at the carbons that are being functionalized, right, it's that middle carbon there, right? It's functionalized with the alcohol and the new carbon chain. Part of retrosynthetic analysis is also thinking about what is possible forward, right? I'm thinking that, hey, I'm going to halogenate here, right, to add my bromine. And guess what? on that middle carbon, right, is where my bromine is. So if I'm going to change it, add functionality, do things with it, right, it's going to be on that middle carbon. So I'm very comfortable with saying that this is the 3-carbon chain. That's the original because I added in this new carbon chain and this alcohol here. So add in this new alcohol and this carbon chain to that middle carbon that is being functionalized by my bromination. Okay? So I'm going to say, hey, this carbon chain here is new, right? So I'm going to cut it off. We can do that little trick again, right? We say, okay, this here is the Grignard, right? So this and then this, right? And then again, where I cut off the carbon that I cut off from, I'm gonna put a positive, that positive next to the alcohol. So very confident that this is a carbonyl here. Okay, so this is my ketone that I reacted to make this. Okay, well, hey, how do I make ketones, right? Oxidations, only one way we can do that. So we get our alcohol here. And so to get from here to here, right, what are we going to do? Again, it's a substitution, so I can cut here, and I can say it's either OH minus or it's water, right? Again, water is going to be our SN1. This is going to be our SN2, but this is also a strong base. This is a weak, or this is a solvent, really, right? Who's more likely, right? Who's more likely? Definitely going to be not that, right? It's going to be that. Okay, got you there for a second, didn't I? Cool. Now, this is a little bit worth talking about because it's possible this might have come up. A couple of you might have learned an alternative pathway to making these alcohols, right? That's through the acetate pathway. So how does acetate work? Well, this guy is a weak base, right? Weak, very strong nucleophile, so it does SN2 here. And then you do hydroxide. A lot of you guys are kind of, I've seen a lot of confusion in the chat about, why is it that this doesn't do elimination? Well, the thing is that carbonyls are very, very electrophilic, especially when it comes to basic nucleophiles. If you're using a basic nucleophile and there's a carbonyl, the reaction is 100% between these two. So a way to think about it, this is completely wrong, but, it kind of just mirrors what you've learned in class, so it can help you out. Is you can think about it like the SOCl2 mechanism where we attack the double bonded center and the oxygen part comes off. Okay, that's what you guys kind of learned in class, right? Which is that when the when the Cl attacks here, or oh shoot, I guess yeah, sorry. So like when the Cl attacks here on that double bond center, right, it just kicks off the chlorine. I think these are the errors you were taught in class, right? It kind of mirrors that, right? I don't really like that depiction, but it's okay for now. So you can kind of think of it that way. So this is acetate substitution. It's sort of like the SN2 type pathway. For example, like, not that this is chiral, but if this were wedge, right, this inverts to a dash, and then this stays a dash. So if there is a conceptual synthesis problem where like you have to, turn something into an alcohol, right, blah, 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 whatever stereo has to change or whatever, then you can use this. But I don't think you guys were taught this explicitly in class, so I don't think you're expected to know it, although I know you guys are seeing problems about it. So I thought I'd talk about it for a second. So either one of these will work. The SN1 is also acceptable. So go ahead and use that, right? I mean, in my opinion, that's easier. So I'd rather just use this. Okay, cool. All right. So hopefully these problems are kind of encouraging you guys or building your confidence. And hopefully they're not teaming a little bit too hard, right? Again, a lot of these organic transformations are going to involve understanding, what can I turn, what can I do? What kind of substitutions can I do? And also like, how can I add like carbon functionality? Again, carbon-carbon bond formation is so important in organic chemistry. I cannot emphasize enough how important it is. Okay, cool. All right. So moving on to these. So these are a little bit more difficult, these last 4, but if you could understand what they're telling you or the patterns to look for, I think you guys would golden on any synthesis problem. Okay, so here's the first one. You can definitely go ahead and try it. Maybe you see where things go, what they're going to do. But yeah, you can go ahead and try this one if you'd like. I'm going to go ahead and get started on this. So when I look from here to here, right, a lot of things are going on. It's not necessarily clear immediately what I might need to do. But again, one thing you can really do that's nice is you can look for functionalities you already understand and break them down. For example, right, I'm noticing that, okay, carbon chain's the same, so not much there, but I do see this carboxylic acid. Guys, we've talked about this, right? Where do these oxidized centers come from, right? They only come from one thing. They come from chromium oxidations of alcohols, okay? Carboxylic acid specifically come from Jones, right? So if you want to know how to write that out, you can go ahead and write this right here, right? This is a very good representation of Jones, okay? But Jones, right, essentially it's adding a carbonyl to that primary alcohol carbon. So I can break this down into this molecule here. Okay, so just from that, I mean, this makes it a lot less complex and easier to look at. Okay, have an easier time understanding what's going on. Now, whether you know what to do next or not can depend, but here's a cool little trick that will pretty much give away how you know for a fact that what we're going to form is what we're going to form. Okay, that trick is what I like to call vicinal functionality. Okay, I kind of mentioned this before with a certain functional group, right? Specifically difunctionality, I should say. So how does this work? We have a carbon with an alcohol, which I can label 1, and we have a carbon next door, which I'll label carbon 2, with an ether function. We have these two functionalities next door. The fact that one of them is an alcohol is just even more of a, it's more of a zinger, okay? Whenever you have a vicinal difunctionality, so a 1-2 relationship between two functional groups, especially if one is an alcohol, the culprit 90% of the time is an epoxide. Okay, so let's remember what epoxides do, right? When I have an epoxide, right, and I open up with a nucleophile, let's say just a basic solution, it opens to the left sub. What I'm doing is I'm adding a functionality to that carbon that I'm attacking, and then forcing the ring to open on the other side, making an alcohol. So every epoxide opening guarantees us a difunctionality or a transformation on two carbons, right? One carbon gets a nucleophile of some kind, and the other carbon gets an alcohol. Okay, if you are lucky enough that your alcohol is already there, you know that that was the epoxide oxygen. So you can very easily narrow down what the nucleophile is, right? Because the other guy just has to be the nucleophile. Okay, so when I look at this molecule here, I mean, you can even see it up here too, right? There is the difunctionality right here, but you know, it's a little more obvious down here. When I see the difunctionality and I notice my alcohol, I'm instantly thinking epoxide and also thinking that this alcohol is going to be my epoxide O. Okay, that's my epoxide O. So I can go ahead and assume that this guy here was my nucleophile. So my ether was formed by nucleophile. I'm going to go ahead and draw him here like that. Okay, so what do I get? Can kind of remove that functionality, but this guy's going to go here, right? So I can go ahead and draw this bond here. But this is my epoxide, drawn a little bit ugly. So let me draw that a little bit better. I guess I didn't really draw it that much better. Is that better? No, it's not. Oh, let's just draw it up this way. Wait. Oh, hold up. There we go. Okay, my bad. It's a little late. Sorry, it's a little late. But this is the epoxide, right? So what I did is just got rid of this guy here and I just drew the chain and, you know, closed in on itself. Okay, but this is my epoxide. Okay, now I can ask myself is what condition did I use to add my ethoxy piece onto the epoxide? So if I look at the epoxide, right, it is on a secondary carbon. If I look at my alcohol, it's on a primary carbon. So because my nucleophile added on a secondary, which is more sub, right, I know that I want to use here the protic version of the nucleophile in acid. Okay, so it's a more sub addition. So use the protic molecule, the protic molecule in acid. If you were to add to the other side, I would just use the basic version of the molecule, the conjugate base. So that's a very good way to determine, right, what to use, right? If you have to use an acidic condition, right, draw the conjugate acid of that molecule and then put it in acid, right? If not, just use the conjugate base, right? And don't put any acid, right? You don't want to do that. Cool. So I know that this here, open up this epoxide. When I'm trying to get from here to here, so here's kind of like the boring part about these epoxide problems, at least for 118A. You're going to have to start from some molecule that is a, 1,2 bromohydrin. So we call this a 1,2 bromohydrin, okay, or a bromo alcohol, because you just use NaOH here and it will close up the ring, right? This will be pronate and this will close the ring. Okay, so this is also kind of a dead giveaway that you're using an epoxide, right? So it's a little boring, but at least we can reason our way as to, backwards how to do this. If we learn this foundation now in 118B, when this question can get asked again, but from a harder standpoint, right? Actually, in 118B, I can start from here and expect you to get from here to here to here. Okay, you'll have an easier time navigating this if you understand the retrosynthetic pathway. Okay, cool. Now, just as a bit of a practice, let's just take this epoxide and let's say that we did it in the basic condition, right? Let's just say that we did it in the basic condition so that it opens up on this side, right? What does that give us, right? We still get our vicinal functionality, right? 1, 2. See that alcohol there. And we get our ether just on a different carbon. So if I were to do my same like PCC oxidation, right, I would just get a ketone here. It'll look like this. Okay, not too crazy, right? Not too shabby of a molecule. I mean, you can still reason your way backwards, right? We see an oxidation, so we go backwards to the alcohol. And then again, we see our 1, 2, where there's clearly an alcohol. So we know that the other guy is the nucleophile. We just work our way backwards on the epoxide. Okay. Now, I will teach you guys this little rule, rule of thumb now so that we can apply it to some other problems. But usually when you see a 1, 2 relationship where one of the guys as that's 1, 2 is an ether, usually ether was added as nucleophile. Okay, we're going to see some examples as to why I say that. Okay, usually it's the ether that was added as a nucleophile. Let's see, is it the next one? Okay, I think the next one, next one gets on that. Okay, cool. All right, so hopefully that one, that's a good one. Actually, before we move on, oh, you know what? Yeah, so I just want to show you guys also, like, what are some other things that could have been there? So, for example, right, we could have kept the carboxylic acid, but maybe we had a CN here instead, right? So when we go backwards, we have this alcohol and we have this CN, right? This would have just been the result of an epoxide opening in like an ACN HCl. Okay, so getting used to that vicinal functionality, right? Seeing that 1, 2 right there, that's one possibility. Another possibility, I guess, is if it was like a sulfur here, right, and an alcohol here, right? That's another one where sulfur opened up. So this would be SH2, or I guess a thiol ether is another good one, right? It's another good one. Okay, cool. So just wanted to show you guys that. Actually, I'm not gonna lie to you guys. I actually have like a piece of paper with some notes on them. I actually took notes for the first time, just for like things that I wanted to mention or make sure, because sometimes I forget. So that's why that was kind of like a weird, like, actually, let me show you this, because I looked at my notes really quickly and I saw I had written that down. Yeah, cool. All right. Anyways, let's move on to the next one. Before our last two, oh wait, no, our last 4 actually. Okay, hopefully we're making good pace. I think it's been like an hour. Okay, cool. All right, let's do this one here. So again, maybe with that vicinal functionality idea, you can try this one on your own, at least try to identify the vicinality and maybe where your epoxide always blah, 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 try that on your own. But let's just get right into it. So like I mentioned, right, clearly there is a 1-2 relationship here, right? But in this case, right, it isn't instantly obvious who the alcohol is, right? It's instantly obvious who the epoxide O is. Now, a very, very common, trap that people fall into is these sort of see the epoxide or the ether O, and they think that that's the epoxide hydrogen. So let's use that, right? Let's say that. So let's say I see this molecule and I think, okay, this oxygen here was my epoxide O. So what would that mean, right? That would mean then that if this was the epoxide O, it would have to be an alcohol, right? So back in the past, it would have to be an alcohol, just like that, okay? And so to do this, right, this is just a Williamson ether process, right? You would have to use a base like NaH and then add in, this part here. So we cut off this part, right? So we add in this part here as like a bromide, okay? And we get to here, okay? Then we can say, okay, this CN here, right? Where does that come from? Possibly just from, opening up an ether, right? So we can do the 1,2 here and say, okay, right, that could have been my 1,2. So I can do this here and say, okay, CN, I added in NaCN, right? Or let's do it this way. I could have added in CN minus, or I could have added in HCN, right? Looking at the position that it added in, right? This is a tertiary carbon here, and this is a secondary carbon here. Okay, looks like we have a tertiary carbon, so more subaddition, so I want to use HCN. A very common way to say HCN is to say NaCN HCl, by the way. This is the same thing. It's what I mentioned before. But we have this here, and then, going from here to here, looks like it's a closing. Oh, okay, so this example didn't do what I wanted it to do. This example actually worked out perfectly. So this will actually work. I can have said that, okay, my ether here, right, works, right? I can cut that off and say it came from a Williamson ether, and then, say that, oh, I added in my CN via, I added in my CN via epoxide opening, and then, this here is just closing of that epoxide, so that works. So I guess I should have tested this one before I did this, okay? But let's also do it from a different perspective as well, okay? Because this one will work. We could also say that, hey, maybe this CN used to be my alcohol. Okay, so maybe sometime in the past, right, my CN was my alcohol. Now, I can't just add in CN, right? I can't substitute an alcohol. That's not going to work. Alcohols are terrible leaving groups. Okay, so I have to turn my alcohol into a better leaving group, right, before be able to do that. So in order for me to say that, hey, that CN was the result of a substitution, right, I could say, okay, that substitution could have been like of a halogen, like a bromine, right? And so bromine, I mean, that is something that I can, make from an alcohol. So that is something that I can make from an alcohol. Okay, and so now I can see another vicinal relationship here, right? This could have been like HBr. Oh, here's an interesting thought, right? So I'm using HBr here, but I think HBr might be an issue. So I want you guys to think for a second, why might HBr be an issue here? So it is true that tertiary alcohols are best with HBr, or HBr is best with tertiary alcohols is really what I should say. But that's usually when we only have a tertiary alcohol, right? We also have another functionality here where you have an ether. So HBr is actually not going to be the best option here because it could interfere with the ether, right? It's like, whoa, that's crazy. I'd never would have thought of that. So in this case, it's actually acceptable. It's acceptable to say that you would use PBr3. That's actually okay. I know PBr3 would do a slow SN1, but it still would happen. It's just really slow, right? Probably just adds a lot of hours to the reaction. But at least PBr3, you don't have to worry about the ether. Okay, so that's a cool little thing to think about. Okay, then we can do that. But anyways, with that idea aside, right? now we've revealed a different alcohol, right? That could be in a 1-2 relationship, right, with that ether. And so we can say, okay, well, in this case, then I have this. And so now when I think about, okay, this was my nucleophile right here, right? I'm attacking either here or here, right? This here is secondary, this is tertiary. Added the nucleophile on the less subside. So I want to use the conjugate base version. Okay, I want to use the this alkoxide here. Okay, remember all basic steps will have a acid workup at the end. So this is also another good way to tell, or another good way to show your grader, like I'm doing a basic step. Okay, and so from here to here again, it's just going to be NaOH. Okay, so I'm actually glad that I went both ways there, that I checked that out, because both ways worked, whether you decided that the alcohol was made from an ether, or you decided that the CN was made from the, or the alcohol was turned to a CN, right? Either way works. And so, that's the great thing about synthesis, right? Is if you have a pathway that works, it works. You'll get the credit for it. Hopefully on your exam, though, that's multiple choice. There's only ever one answer. You don't have to worry about multiple answers. Okay. So what was that point I was trying to make, right? Why was I trying to make a point that, sometimes it's, the ether is not the best thing to use? Well, let me just slightly modify this. Okay. Let's say that instead of my endpoint being the nitrile, my endpoint was the bromine. Okay, and so I do that same idea again, where I say, okay, let's think of if this guy here were added in, right? So let's say that I did this. Okay, again, this is the new piece, right? So then as an alkyl bromide. But what might be the issue here? What might be the issue with this synthesis? Well, for those of you who can't see it, the issue is that the second you do the deprotonation here, right? Yes, we are hoping that we get this SN2, between these two molecules, but there's an SN2 that's faster, right? That's going to be the epoxide forming SN2. So in this example, right, this is not going to work out too well, because forming that oxide is just going to reform the epoxide that we just, that we had in the beginning. Okay, so not the best idea. So you can actually think that, this to this would be a very good trick synthesis, right? A very good conceptual synthesis, because it tests your ability to see, oh, this to this is not, it is not a Williamson ether synthesis, right? Because it's going to just form the epoxide. Now, that's not a totally bad deal, right? Because if I form the epoxide here, right, we can think of a way of getting from here to here, right? Where instead of now saying that the alcohol was made from the ether, maybe the alcohol is made from the bromide. Yeah. So now we're going to say, okay, well, obviously this guy didn't work out in being the alcohol, so maybe the bromide will. Well, how do we make bromides from alcohols? That's just, HBr, PBr3. Again, we talked about this, why PBr3 would probably be the better choice on the center. But now when I have my 1,2, right, again, right, I have an ether that's adding on a secondary. This is a tertiary. So my epoxide here is going to open in basic condition. Okay. So this is an example where, hey, the ether is not such a great idea. So I guess the lesson here, right, the lesson we want to learn is when you're choosing, two possible groups, or one between two possible groups that could have been your alcohol, right? Try both ways. It's possible that both ways work, right? It's also possible that one way is just really bad. Whenever it's an ether, usually the case is the ether is not the best option, but I guess we just saw a case where it is. So I would highly recommend, right, logic your way through which pathway is better, right? Work backwards on both of them and look for any sort of indication of a bad step, right? We just saw what the bad step for this one was, right? If I want to assume that this alcohol here, right, went from here to here, and that NaH step and Br step, right, I need a good reason for why OH will not collapse onto that bromine. right? Answer is that there really is no good reason, right? So seeing, having the ability to see that when you write it out is really going to help you out. Okay. That's also the point of doing these practice problems, right? Is it really helps to hear or see someone talk through this so that it kind of helps build your idea of what you should expect or what you should know. Okay. So I'm just praying that something that I draw or something that I write just ends up showing up, right? That would just be great. Okay, cool. All right. Now, again, just like I did with the last one, it doesn't hurt to just see what other things could have looked like, right? Like, for example, could have had like an N3 here. That's a weird one. We haven't seen N3 in a while, right? That's not one we've seen quite in a bit, but it could have been an N3 there. Oh, maybe we, I mean, I guess we've already done this one, but I guess we could have, this is actually an interesting one. Let me actually try. I just thought of an interesting one. Let's say we did this. Let's say, okay, hold up. I can't remember if any of the next ones has this. So I'm going to change something about this. Let's say we had this though. This is an interesting one, right? This is a very interesting one. Okay. So this one, take some time on it. Could be a fun one. I mean, I'm just thinking, I don't know if it's even going to work, but let's see. So in this case, I've taken away that methyl from this carbon center, right? So obviously we're forming a CC bond. So I'm thinking that we're doing some kind of Grignard process. Now, as of right now, we've only talked about Grignard from the carbonyl perspective. So, it might just be useful to think about it that way, right? So this is our original carbon chain, right? This is our new carbon chain, right? So maybe we just think about this from a carbonyl Grignard perspective, where we say that if this carbon is adding to a center, right, it's probably to that alcohol center of a carbonyl. So first off, again, Grignards, right, they mean, they need alcohols, right? They make alcohols. So where in the world is this CN coming from, right? Well, obviously I can't say that OH was turned into CN, but I can say that Br was turned into CN. Okay, so I can say that this was the result of like a really slow SN1, right? And then this was the result of, again, PBr3 because of that ether, pesky ether, right? But from here, I have an alcohol, which is great, right? Because now I can say, okay, this is my new carbon chain. I can just cut that off. And what I get, again, where I cut that guy off from, so this would be CH3. I'll put Li. We haven't used Li in a bit, right? But we can say CH3Li, right? And then H plus. But again, I put a cation from where I cut right underneath the alcohol, so it's going to be a carbonyl. Okay, and then I have this guy here. Okay, so this was my Grignard process to add that one carbon in. Again, where do carbonyls come from? Carbonyls come from oxidized alcohols, right? This shouldn't be anything new anymore, right? And so from here, right, I can imagine that I have a 1, 2, right, where this is clearly my epoxide O, right? So like this. And again, this is just NaOH to close this up, right? Or NaH, that works too. Doesn't matter what you use, doesn't matter. But from here to here, right? Oh, I guess, okay, so there is a bit of an interesting issue here, right? How in the world do I add, like selectively add this guy here on, I mean, these are both secondary, right? So we don't know where it goes. So in a case like this, because I'm working backwards, I mean, I guess I wasn't thinking about it. I'm going to do something. I'm going to do that. That makes this problem easier. So I apologize for anyone that paused and tried this and were like, oh my God, this is impossible. It's not that it's impossible. It's just that I didn't really think backwards, right? I just did it on the spot. But also you can make a good argument, right? This is a methyl, this is an ethyl. So on the sterics end, you might get a little diastereotype selectivity, right? You might get that addition there, but you can use any condition here, honestly. In the case of equal substitution where it's symmetric, use whatever you want. I'm just going to use the O minus. Okay, so that's a cool little problem there. gets the brain juices flowing a little bit, a little more. I like that one. That one is a fun one. Okay, cool. All right. So getting into epoxides, hopefully seeing that 1-2 vicinal relationship a little better. Okay. All right. So moving on to these two before we get on to our two fun ones. Okay. Yeah, let's do this one first. So again, we can kind of see what I'm trying to get at here, right? Because I'm forced to do this, right? There's no choice. Because I don't think you guys learned what MCPBA is. I guess someone should let me know if you guys learned what this is. I actually don't know if you guys learned what that is. I don't think you guys did. But go ahead and try it if you want. I see a lot of things going on. But without further ado, right, I'm going to take my stab at it. Looking at this, I noticed two things. Okay. One thing I notice is that I have two new carbon chains. Right. So I have these, sorry, let me use my usual color, right? My blue color. I have these two new carbon chains. I mean, clearly the original carbon chain is the ring itself, right? But what might be really, really, really weird here is that I have a carbon chain on the same carbon as a bromine, right? Which that's easily logical, right? I can just say, okay, where did this, I mean, if I had a carbon chains, I need an alcohol, right? So I can easily go back to this alcohol here, right? I can just say, okay, let me cut this bond off, right? That's easily that bromine there. So what? HBr, boom, easy, right? No ether to worry about. But wait a minute, right? When I think about my two disconnections, I have a carbon chain that's farther. Wait a minute. I added a carbon chain that's not on the alcohol, right? Like, for example, this guy here, I could say, okay, cut here. That would just be what, CH3 Li. Right? And I could say again, the cation is here. So obviously it's a ketone. But where in the world did this carbon chain come from? Right? Actually, let's do one more step. We can do the PCC. We can undo the PCC here. Right? We can say, okay. There. Okay. I have my alcohol. Where in the world did this guy come from? Right? Okay, you must have made a mistake, right? That's a possible thought, but this is not a mistake. Okay. This here, this Grignard addition, that's not on the oxygen carbon, the alcohol carbon, right? If I cut here and I use my same little trick where I say, okay, this must be my Grignard then, right? And I draw the positive where I make the bond cut. If I were to think about these alcohol lone pairs, right, next to that cation, oh man, that cation is not surviving 1 second, right? That alcohol is going to collapse on it. If I draw the result of that closing, of that attack, what is the structure that prevails? That is the result of an epoxide adding to a Grignard adding to a epoxide. Okay. So now we know what the relationship looks like for a Grignard adding to an epoxide. Okay. Couple of ways to think about it, right? One way to think about it is that the carbon chain is adding a little bit farther away from the alcohol, right? It's one carbon down, right? I guess we can use that too, right? If I think about my vicinal functionality, right? My functionality here, or my my transformation is vicinal to the alcohol, right? It's not on the same carbon as the alcohol. It's vicinal to the alcohol. So another way that gives away the epoxide, right? The last way that's a bit more of like a trick way is when I do that positive cation cut, right? That positive is not underneath the alcohol, it's next to the alcohol, which is indicative of an epoxide opening. Okay, so 3 different ways you can kind of think about it, right? All lead to the same answer. Now, obviously, this here is just like NaH. Okay, but this is like the most powerful Grignard usage because it's a little hard to see, but it opens up the library of reactions that you can do, right? Library transformations that are possible, right? Makes it, makes you feel a little more alive. right? So cool little epoxide transformation, right? Not only can we add to the same carbon as an alcohol, we can add vicinally, right? As long as we are using the correct functionality to do so. Okay, cool. So that's a fun little one there. All right. So if I look at this one again, I can look at a couple different things, right? I mean, I see that this is the original chain here, right? Again, where am I seeing my functionality, right? I see a new functionality here, right? I see a new functionality here, the CN, and then right next door, right, vicinally, I see a new functionality there, right? If I were to imagine, okay, I added a carbon chain, right? So I must have done a Grignard. So the CN must be from a Grignard. I use CN too much. I didn't really think too hard on this one, did I? So this would be like a CN minus step. So this would be PR. And then again, if I'm doing a Grignard, right, that must mean I had an alcohol, right? So I do like an HPR or a PBR 3-step. Either one will work. In this case, either one will work, right? Again, thinking about, all right, this is my original chain, and this is my new chain, right? It is vicinal to this alcohol, right? It's vicinal to this alcohol. It's next door to this alcohol. If I make my, Grignard cut, right? Say that, okay, this guy here gets a positive. The cation is next door to the alcohol. All of these symptoms of an epoxide, okay? And so obviously from here to here, we can do our little closing, okay? Cool. So I'm trying to think of if there was anything else. I guess there could have been like an N3, right? I don't really have much else in my notes, to be honest. Been kind of covering everything, I think, that I wanted to talk about. So this kind of leaves our last two problems, I suppose. So just to kind of, not really recap, but to just kind of go back and look at these, right? A lot of these problems, right? They're all here to show you some pattern, right? They're all here to get you accustomed to what are usual reactions, right? Like alkane chains, I'm brominating usually, and maybe I'm substituting, right? Eliminations, not too fun because eliminations are dead ends, right? But I can maybe do Grignards and do eliminations, right? That was kind of the point of this one, noticing that there, okay? Or, this guy here, like I have a square, crack it open, right? Crack that square open and then, do your, add your bromine functionality and do your substitutions, right? Grignards obviously being a big thing, right? You may being able to mess around with functionality. I mean, honestly, the word, the funniest thing she could do, honestly, is she could take this and then do do that water wash thing. Like imagine like this would be like a sick joke, right? If like the point of like she said to go from here to here. Right? Like how, I don't know if this would be difficult, but it's like, how terrible would that be? Right? If you had to go from like here to here, right? I guess you could still track the fact that you're doing an alcohol reaction, right? But you'd have to realize that, we wiped out functionality. The only way to do that is with the MgCl synthing, right? So like this would be Mg and then H2O. I think it'd be fair, if they put the deuterium there, so that at least you could track what's going on, right? Like, you turn it into a deuterium, at least you can think, oh, you're doing that Grignard quench like synthesis thing. So it's sort of turning your eye to that. That would be really funny, by the way. And then the epoxide vicinal relationship. I'm crossing my fingers that you guys get an epoxide. I mean, that'd be great. Epoxides are fun. They're great. They test a lot of things, and they're really easy to see once you know what to look for. Okay, cool. So with that being said, we're on our last two problems. A couple of you guys already tried this one, which is great. I just, I wanted everyone to be able to see it and, understand it, because actually this here, right, from a different starting material, this here is a 118B final synthesis. So if you can do this, you can go to your 118B or 118C friends and say, hey, I did a 118B synthesis and a 118A, right? What were you doing? Probably picking your boogers, right? So cool. So we can do these here. This is sort of like a proof of concept, I think, or just like a cool one that I just thought up on the spot. I don't even really know if it works. I just thought it'd be a nice one to do. But we have a cyclic ether and we have a cyclic ether. And it looks like we just added carbons to it. So it's like what gives, right? What's going on here? Well, if I kind of think just outside of the box for a second or outside the ring, all we really learned for ethers is that we can crack them open, right? I mean, obviously with epoxides, you can do a lot of fun things, but when it comes to just normal 6-membered, 5-membered ethers, like all we can really do is crack them open. And what we're also doing is forming new CC bonds, right, on both sides of this on both sides of this ether. So I'm thinking I just crack open this ether for a second. So actually, interestingly enough, I'm actually going to work a little forwards here. Okay, so I just crack this open to something like this, right? So at least I'm using H2SO4 here to some extent, right? But when I see this, I'm thinking, okay, well, I cracked it open and I want to make CC bonds on both sides. So I want to make a CC bond on this carbon and a CC bond on this carbon. So the most logical nucleophile to use would be water, because if I make this water, then this becomes an alcohol. And now I have functionalities that I can add carbons to, right? Because these alcohols, I could just do a PCC on, and they become aldehydes, right? Which I'll kind of draw better here. 1, 2, 3, 4, 5, 2, 3, 4, 5. And now I can go ahead and add my, add my 2 carbons. So I can do like a CH3Li. Right? That will turn both of these into alcohols. I'll put excess here as in terms of like there's just a lot of it, right? I can do PCC again. And then I could do, excess CH3Li again, right? To here, okay. Now here's where you have to be a little clever, right? How do I, 1, 2, 3, 4, 5, 6, how do I close this up, right? Well, this is kind of like a Williamson ether, I suppose. I guess you can kind of think of it as like that. But the idea here was just, okay, what I want to do is close the ring. So I just have to motivate, right, this OH to kick off this OH. The way you could just do that is H2SO4, right, and heat. So kind of like a dehydration reaction. But I guess since you want to be careful here, you'd have to do it like 60 degrees or anything below 100, right, to prevent the elimination. So what this would do is turn this into a cation, right? And then this alcohol here is just motivated like hell to just go ahead and close up on it. Okay, so this was more of just like a proof of concept, just a fun little one to do. It looks, surprisingly, it looks like very like weird, but it's a very simple, synthesis to do. So that was just a fun one there. Again, ethers are not very synthetically useful, honestly, because you just crack them open with, hot acid. You know what? Actually, I don't know if I should. I guess this is a cool one. So for anyone who gets this far, I suppose you could try this out. It's a cool little proof of concept. I don't know. I keep saying proof of concept. I don't know why. But it's a cool little like mechanism test. But it's not actually true that ethers are inert. It's not actually true at all that ethers are inert to base. THF, which looks like this, actually, if you put it in Bewley above negative 78 degrees, so negative 78 is a very low temperature. It is usually like it's the combination of dry ice and acetone. So like whenever we need a really low temperature in the lab, we just like automatically use this combination. But if you ever have Bewley, so Bewley is a butyllithium, so it's a base, very powerful base. If you have Bewley and you have ether above this temperature, actually, you will see a decomposition. Okay. The decomposition products look like this. Okay, so if any of you guys want to try this out, you can, but this is the reality of it. Ethers do degrade to bases, but usually at like a very higher temperatures than we normally have them. So if you want, go ahead and try this out. The only hint that I'll give is that this is a base. So look for the most acidic proton and pull it off. Okay, so pull off the most acidic proton and try to figure out a way to turn it into this. Okay, cool. All right, but again, ethers are not very fun synthetically. Kind of a bit boring. So really, this is like the only chemistry you can think of doing with it. Can't really think of anything else you'd want to do with it, to be honest. Okay, cool. All right, so last one here. Go ahead and try it. It's not hard, I would say, but it's a fun one. You have to think a little bit outside the box for this one. Cool. So again, we can kind of see our, carbon chain here. And I think that I might have trained a couple of your eyes to see things, right? Like I trained your eye to see the OHBr and think epoxide, but I'll tell you right now, that's not what we're going to do. Okay, well, that's our original chain, right? Our new chain is this guy. So we know we did a Grignard, but again, Grignard means alcohol, right? There has to be an alcohol. So we could do that same thing again where we notice a pi bond and we think, okay, that pi bond could have been the result of some kind of dehydration. Right, so it's like, no, I just put 180 because I know that's high enough. Okay, and so there's sort of, again, two alcohols that are possible here. Okay, so two possible alcohols that this could be, right? Two possible alcohols. Now, one of these is actually going to be better than the other. And to be honest, the only way to know which one is better is to kind of choose one and kind of pray that you get it right. So, it could be either one, but you know what, just to make, just to kind of give you an idea of how to, save yourself, I'm going to purposely choose the wrong one and work backwards on it and show you where I get stumped, right? Or where things don't start to make sense to me. So the wrong one is when the alcohol is here. Okay, cool. So let's say the alcohol is there. Again, the new chain is this guy here. So what I can do is just cut here and say that, okay, well, if the, this is my Grignard, so this is my Li reagent, right? Then over here must have been, again, I have the alcohol, right? This is where I cut the bond, so it's going to be a ketone since the cation was under, right? Uh-oh, here's my issue. How do I make sure that this is the ketone that's attacked? If this is the pathway, right? This could be the pathway. How do I make sure that's the ketone that's attacked? Because this one could also be attacked, right? If I think about it, right, there's a methyl on this side and ethyl on this side. I feel like this side would be more favored. So right off the bat, I see an issue, and I don't like this. So instead of putting the alcohol there, I'm going to try putting it on the other carbon to see if it helps, right? Maybe solve an issue or something. And so maybe now I do this. So these are my new carbons, right? But this time the alcohol is on the other carbon. So when I break this, interestingly enough, right, because the alcohol is on this carbon chain, actually my cation will be here, which means that my carbonyl reagent is this guy. And actually my Grignard then is here. So interesting. I made a Grignard from this carbonyl compound, which again, we haven't really done a lot of like making the Grignard problems. I guess that's my fault. I didn't really think of doing that. But usually that entails, right, Mg ether, right, to this. And so now you can kind of see, okay, right, if I made my Grignard from this, then this guy must just be a PCC oxidation. Okay, so this is a really cool problem. You're adding a Grignard that has a carbonyl on it onto another molecule with a carbonyl. And you can notice that there's a little bit of symmetry, right? This molecule is basically the same thing without the Grignard on it. So one good question is, why doesn't this Grignard just start chain reacting with itself, right? Why is there not just a chain like this, right? Where a bunch of these, I mean, like a polymer of these guys, right? Where like this guy reacts with this guy, and then maybe there's an MGBR here reacts with the next guy. Okay. Well, what's interesting about this Grignard is that this Grignard is very resonance stabilized, right? If I sort of draw the anion here, this anion resonates with oxygen, and therefore it's a lot more stable than, say, a Grignard that's just a carb anion like N-butyl, right? A butyl lithium, this is super unstable, right? pKa 50. This guy here, though, pKa of 20. So look at that, drops 30 units being next to that carbonyl. It's incredibly more stable. So this actually here has a name. This is called an enolate. And this is something you'll explore in 118B for the final. Okay, but we don't need to know all that stuff right now. All we need to know is that, hey, I can do this reaction where I can turn this into an enolate that's stabilized, and it won't really go willy-nilly attacking everything. Now, what's even more cooler about this is that I can make this reagent here from the bromo alcohol. Okay, you just have to be clever. You just have to be clever. Okay, how can I make this guy into this guy? Well, hey, I have to get rid of the bromine here, right? Or I have to turn that bromine into a hydrogen. So how might I do that? Right, we just talked about this. We can turn hydrogen to bromine and also reverse that functionality, right? We do that with Mg ether by turning this into this. And then usually we add in water. But what's really cool about this, right, is if you think about it, you can actually quench your Grignard with the protic alcohol that's right next door, right? This alcohol is just going to react instantaneously with that Grignard. It's going to make an oxide that just gets protonated in your workup, right? So we'll make this. So you don't actually have to use water. You should still show it, but it's cool that it kind of quenches itself, right? So you make this, and then you can just do a PCC oxidation. Okay. So cool little reaction there, right? Does something that we don't really expect. Okay, cool. So fun little reaction. This is like a Coleman. I mean, this is like a really, really like challenge question, right? Like this is like if Nasiri really wanted to make your life hell. Not really. That's not true. This would be something that if I wrote the exam, I would write this as the final question because I think it's totally fair. Okay, and it kind of reveals to us something that I guess I didn't really think about is turning our reagent into a Grignard, right? And then doing a reaction, which you can totally do, right? I wouldn't be surprised if that would show up. Okay, cool. So I was actually going to call it, but I just realized I looked at my notes and there's one example that I don't know how I missed it. I wanted to talk about this one, so we're gonna do that one example. We are going to do it. It was something that I saw in the Discord, so I wanted to do it. I think something like this. Okay, and then after this, we'll probably just call it. Okay, so I saw this synthesis getting thrown around a lot, and I know it was talked about in a different video, but I just wanted to provide a way to think about it, right? Help you guys, logic your way through it. Okay, but this is a synthesis where we're making an epoxide from something that's not a bromohydrin, right? So usually we say that epoxides are made from bromohydrins, but we're starting from this material here. So it actually kind of helps that we know that these are made from bromohydrins, because then we can immediately say, okay, I know that then, right, this intermediate is what's possible. Okay, I know that this intermediate is possible, or I guess it could have been the other way around. I'm just going to kind of go a little faster this so I can end this off, right? Because I think we're nearing the 2-hour mark, and I didn't want to do that. But anyways, I know that epoxides are made from bromohydrins, so I can surmise that it's this bromohydrin here, and then I can kind of match, like, how would I get from here to here, right? It looks like I reduced and I turned the OH into a BR, right? So what order do I do that in? Well, let's say that I reduced first. So let's say I used NaPH4 CH3OH, right? You would get 2 alcohols here. And then when you do like your PBr3 or your HBr, well, you're not going to be able to control who reacts, right? First off, if you use PBr3 here, right, there are 3 BRs on PBr3. You're going to get both of them to react. So this is not going to work because you're going to make the dibromide. Okay, so that's not going to work. If you use HBr, Okay, because you might think, okay, maybe I'll just use HBr because there's only one Br. That's also not going to work because when you create this cation, right, something cool will happen. You will actually get a hydrate shift. Okay, so you'll get a hydrate shift so that this alcohol is underneath the cation. And then, like we've talked about before, whenever the cation's underneath an alcohol, turns into a carbonyl. So you'll actually make a ketone from this reaction. So, that won't work either. Whoa, right, crazy. Didn't think of that one, did you? Doing NABH4 first is not good because you're reducing selectivity on that alcohol to bromide, and you're also possibly making another side product with it. Okay, so you should make the bromide first. I would highly recommend making the bromide first. I mean, you should. So HBr here. PBr3 will work too. It doesn't really matter. Okay, and then just do NABH4. Okay, and then CH3OH. Okay. Now, I know that this reaction is written like this, and mainly because of retrosynthetic analysis that we got to this, but it is actually very likely that this proceeds here, because remember that when you do a reduction, right, you're making an O minus. That O minus will almost instantaneously react with that bromide. So you probably don't even need to really worry about this here. Doing NaH, it will probably just, this is like an intermediate, it will probably just immediately go through. Okay, cool. So with that being said, looks like, let me just check my notes one more time. It's so hilarious to me that I wrote notes. I normally don't do this, but since this is my thing, so I just wanted to make sure I went through all the examples that I wanted to. But with that being said, that should be all the examples that I wanted to go through. And hopefully those examples really open your eyes to retrosynthetic analysis and how we can apply it to synthesis and make it a lot easier, right? It's a patterns game. It's all about patterns, right? Understanding what kind of reactions I could do, right? In 118A, it's all about substitutions and eliminations and epoxide openings, right? And Grignards. Those are like the four main like reactions, right? Or really should be three. It's Grignard substitutions and eliminations. That's the name of the game. So understanding when to use when and how to use each one will really help you out. Hopefully our discussion today has helped you out with that. I'm trying to look in here and see if there's any cool like Grignard thing we could have done that I didn't get a chance to do. Oh, yeah, I guess there's a cool thing here, right? Like in the intermediate where I guess you could have an intermediate here where, well, could we? Okay, let's say I could get to this point here, which is possible from this here. Yeah, there actually is. So we can make the epoxide, open it in base, right, and get to here. And then I could do an Mg. Remember, ether's inert, so I don't have to worry about the ether. I guess I could have also, right, either I could have added in a carbonyl with two R groups on it. So I could have done something like that, or I could have added in an epoxide. Okay, so I could have added in a carbon or epoxide, right? So how could I break in this molecule down to kind of understand it a little more? Well, I could have noticed, right, that there's an alcohol, right? So actually, first I could have noticed is, okay, this is the main chain here. So I could have labeled that. And then I could have said, oh, okay, look, I added in this fragment here, right? Or this fragment here. Right, and I could have done that disconnection. And again, could have used any rule that I wanted to, right? But probably the easiest one is where I make that disconnection, right? I could have put a cation on that alcohol side, right? In this case here, the cation is underneath the oxygen, so ketone. Here, right, this connection is the cation next to, right, the alcohol, so epoxide. And that would tell me that this here is the Grignard over here. And I could have went back here, back here, and back here, back here, right? Because again, Grignards can again, only be made Mg ether to back to the bromide. And then again, okay, I guess we play that game again, right? But we already played this game, right? Of who is the alcohol. And we talked about how if I try to make it from the ether, right, not compatible with the bromide. But if I made it from the bromide, right, it's a bit easier. So PBr3, again, HBr messes with the ether. And then I could do like this opening here, and then NaOH. Okay, so that's a cool, like another cool application, right, of that, of epoxide versus carbonyl, right? Again, it's all these fun little examples, right? Yeah, cool. So actually, you know what? Just for the sake of time, I'm just gonna cut it here because, you know, Wednesday people do need time to watch this. It's probably already 2 hours long. So yeah, if there's any questions, let me know. You know, I'll be honest with you guys. It is like 4 in the morning right now. So if I made errors, it's very likely. Just let me know, and I will address those. Okay, cool. All right. Have a good one, guys. See ya.